Some motions can be quite complicated. Now, for example, we have talked about parabolic motion for some point. That's very simple for a point. But just imagine if you throw some three-dimensional object in air, then how will it move? You can see it throwing on your own. You can possibly throw a pen and see what happens to it. It would be somewhat complicated type of motion. So then if you watch out for some particle, then it becomes non-parabolic for that particle. For example, if in this object, if you look at the top, just focus on the top as this motion goes on, and that motion would not look parabolic for that particle. And likewise, it is the case for many particles in that body, most particles in that body. So we cannot say that these particles are performing parabolic motion, but thankfully there is some particle here which does follow parabolic motion. There is some particle inside it. In some cases it does not have to be inside the body also. So let me just say that there is some particle which does perform parabolic motion if you throw some non-particle object. Here comes the concept of center of mass. In the body, there is some point, and that point can be treated as particle. And a very good way to find the center of mass is to try to balance. If you keep the object too much on one side, it will fall. Too much on the other side, it will fall. But there will be some point at which you should be able to balance it. And that should be the center of mass of that body. So the idea is that we are trying to simplify a three-dimensional body motion by trying to find some equivalent point. That equivalent point, of course, cannot tell us everything. It cannot tell us about the complicated motion of other particles necessarily, but it can still tell us many things. That makes it very useful. Now that was just to give you an idea of the concept. There is the definition for center of mass. First, we talk about a cluster of isolated particles, M1, M2, M3, M4, and so on, and some observers or some reference point O. M1 is at a distance x1. In fact, I should say M1 has the coordinates x1, y1, z1. M2 has the coordinates x2, y2, z2, and on now. Then with respect to this O, the center of mass of this system will have x coordinates m1, x1, m2, x2, and so on, divided by M1 plus M2 and so on. Likewise, YCM, M1 Y1 plus M2 Y2 and so on upon M1 plus M2 and so on. And ZCM also. Right, so this definition is fine when you have discrete particles, M1, M2, M3, discrete. But when you are talking of smooth three-dimensional objects, then this is not really comfortable. In a smooth continuous object, where will you find M1, M2 and M3 and so on? So we will talk about that case later. Clearly, a case of discrete particles, and there is no need for Z. It is all about XY plane. So ZCM will be 0. Z1, Z2, Z3, Z4, they are all 0. So ZCM will be 0. XCM would be M1X1 plus M2X2 plus M3X3 plus M4X4 divided by M1 plus M2 plus M3 plus M4. Let's call M1 as M into 0, 2M into A, 3M into A, 4M into 0 divided by M plus 2M plus 3M plus 4M, that is 5MA upon 10M, that is A by 2. So that's XCM. Now YCM, can you find out YCM like that and tell me how much you are getting? A by 2 is not possible. Heavy things are towards the top side. If the pen is heavy on one direction, you will have to take your finger to that side. So 3M and 4M are towards the upper side. So YCM clearly must be more than A by 2. So 7A by 10 is correct. So if you look at that figure, A by 2 and 7 by 10 should be somewhere here. If you see left right side, it is not favoring left side or right side. Why? Because left side 4m plus m, 5m is there. Right side 3m plus 2m, 5m is there. Right and left are balancing each other. So it is at the middle. But if you look at this middle, then that middle is not possible because left side you have 7, right side you have 3. So it won't be at the middle, it will be shifted towards up. Center of mass favors the heavy side. But if everybody is equally heavy, then it will be absolutely symmetric. Try this on your own. Your answer must be with respect to something. Now just to make sure that everybody takes the same reference, I'm telling you this. Take A as the origin and AB as x axis. Let me check. You are getting 1/3, half. You will need to recheck. The answer I have is 7/12, √3/4. If you would like this to be discussed on the board, raise your hand. One kg is at 0, 2 kg is at 1 meter, 3 kg is at x equal to half. Sum of masses 7. Then YCM 1 kg is at 0, 2 kg is also at 0, 3 kg. What is the height of equilateral triangle? Height of equilateral triangle? √3 by 2. So divided by 6. Now, just simplify and see if you are getting the answers. Any questions if you have, then let me know. I'm just showing these as a group, these are the group, but that's not necessary. That's not necessary at all. There are m plus n particles overall. And we want to know the center of mass. So that's no big deal. For this, now m and m will create some confusion. Okay. Maybe n1 and n2. So m1, x1, m2, x2 up to mn1, xn1. Or maybe dash and without dash. Divided by m1 plus m2 plus m3 up to mn. That's not complete. After this, we have to start from here. I'm using capital for that. Or maybe I can use n plus 1. N plus 1. Then I can continue with small m. N plus 1. So this 1 is actually n plus 1, n plus 2, m n plus 1, x n plus 1, m n plus 2, x n plus 2, and this will go on till m n dash x n dash. From m1 to mn, this sum I'm calling as capital M1, and that sum capital M2. We can use sigma notation MIXI, where I goes from 1 to 1 to n plus n dash. In fact, here look at the last term again. This should be n plus n dash. There is slight problem due to the space. Maybe I can remove this term. mn plus n dash x n plus n dash m n plus n dash. So I goes from 1 to n plus n dash divided by m1 plus m2. Sigma can be split up. We can add from 1 to n, and then we can add from n plus 1 to n plus n dash. If you look at the left cluster alone, its own center of mass would be this. Left cluster alone, its own center of mass will have x coordinates equal to this. If you look at the right cluster alone, its own center of mass will have x coordinate equal to this. See if you are able to understand these 2 points. If you have any questions about them, just let me know. First, we considered whole of them as having center of mass, x coordinate of it as xc, whole. Then left cluster alone, x1, right cluster alone, x2. We are discussing about x coordinate. Likewise, we can extend our discussion to y coordinate and z coordinate. Now, in place of this sigma thing, I can put m1 x1 here. So xcm would be m1 x1 plus m2 x2. Look at that. Divided by m1 plus m2. That's a very powerful result. If you have just two particles, one particle called m1. Please note, I am calling it particle. Actually, M1 is not, capital M1 is not a particle in our discussion here. Capital M1 is the sum of all masses of the left side cluster. If M1 is a particle, if M2 is a particle having x coordinate as x1, having x coordinate as x2, then for this system of two particles, xcm is given by m1x1 plus m2x2 over m1 plus m2. Isn't it interesting? It is effectively speaking that you have replaced the left cluster of particles by just one point called m1. And where have you placed m1? You have placed m1 at the center of mass of the left cluster. It is like you are replacing the left cluster by capital M1. Imagine one galaxy having so many particles in it. Actually, they are not particles, they are huge fellows, but from Earth they look like particles. So you are replacing the whole galaxy having so many particles by just one particle, and that particle is kept at the center of mass of the galaxy. Another galaxy, M2. One particle at its center of mass, M2. And for these two galaxies, we can find the common center of mass for the two galaxies, which is given by M1x1 plus M2x2 by M1 plus M2, I mean x coordinate. Likewise for y coordinate and for z coordinate. It's a very powerful result. So YCM and ZCM similarly. So replacing a group of particles by just one equivalent particle placed at the right location. Any questions? Let me know. This result that we discussed, we might have discussed it for cluster of particles. This result will work for some bodies also. So it's a general result. Say, it will work for continuous bodies also. Say for example, you have got some L-shaped object kept like this. It's a continuous object, as you can see. All dimensions are suppose given to you. All dimensions that you need are given to you. You have to find center of mass of this L-shaped object. I suppose it L. So you can break it into clusters or segments. One segment maybe can be this. You find its center of mass. Maybe it comes somewhere here. That is for this part. Now you consider this part. You find its center of mass. Maybe it comes somewhere here. So you are replacing this whole thing by one particle. You are replacing this whole thing by one particle. Mentally you erase these fellows. This is gone, this is gone. Now you just treat two particles. As simple as that. And for two particles, discrete particle formula you can use. So this discussion is valid for whether you have isolated particles or you have continuous bodies, replacing them by equivalent masses. Your answer needs to be very clear. With respect to what? Center of mass is a point, it's a coordinate. So it is with respect to somebody. With respect to AB, you are, when you say with respect to origin, is origin a straight line? When you say with respect to somebody, it's a point. So what's your origin? What's the origin? On CD line 3 by 4L away from D. Okay, that makes some sense. So I look at D, 3 by 4L away from D on the CD line. Yes, that is clear. Let me see. Yes, it is the correct answer. If anybody would like this to be discussed on the board, then raise your hand. Okay. The center of mass of uniform rod is at the middle point of the rod. So AB rod we are going to replace by a point kept at its midpoint. See, rod AB is gone. A particle comes in its place whose mass is the same as that of the rod which is kept here. Then rod CD is removed. It is replaced by a point whose mass is m itself. It is placed at the midpoint. Now, we have a symmetric case. So, center of mass has to be at the middle point here. This was L by 2, so it should be L by 4, L by 4. So, your answer could be, with respect to C, along CD, it would be at L by 4. That could be one way to give the answer. Any questions? Let me know. Brick is homogeneous. Homogeneous means its center of mass would be at its geometrical center. So replace one brick by a point, another brick by a point, another brick by a point, on and on and on and on. Now when you replace them, they are gone, deleted. So delete this, this, this. When the points are coming, these are being deleted. In y direction, if you see, then with respect to this line, right and left balancing is there. With respect to this line, right and left balancing is there. So YCM has to be this height. Okay, but width is not given. Let me say that width or height maybe. Each of length L and height H. Yes, now we can answer that YCM should be H plus H plus H plus H by 2. 3H, no, 3H plus H by 2. Now that's the common sense approach. If you want to do it by the formula, that way also you can find YCM. And that way you would do it like this. First, mass into its y coordinate, which is H by 2. Second mass into its y coordinate, which will be H plus H by 2. Third mass, its y coordinate, H plus H, 2H plus H by 2. And likewise you can complete dividing by the sum of all masses, 7m. Just see if you get the common sense answer or something different. 7h by 2. See if you get that answer. Okay, now XCM. First fellow is at L by 2. Second fellow is at L by 10 plus L by 2. Then third fellow is at 2L by 10 plus L by 2. Fourth fellow 3L by 10 plus L by 2. Fifth fellow and this fellow are identical, 2 times. Sixth fellow and this fellow are identical, 2 times. Last fellow and the first fellow are identical, 2 times. Whole divided by sigma of masses. Let's find it out. Any questions? Let me know. Yes. Exactly. That's assignment problem. Question. We stop at this point.